Welcome to Io, the innermost of Jupiter's 4 Galilean moons, and without a doubt, the most violently, aggressively, and relentlessly active geological body in our entire solar system. For a very long time, humanity's understanding of moons was based almost entirely on our own. We believed that small celestial bodies, lacking the immense internal heat of a planet, were destined to cool down quickly after their formation. We thought they were doomed to become silent, frozen tombs, scarred only by the external impacts of asteroids and comets. That assumption was shattered forever in March of 1979. When NASA's Voyager 1 spacecraft flew past the Jovian system, a navigation engineer named Linda Morabito was examining the images and noticed something impossible. There was a massive, umbrella-shaped anomaly protruding from the edge of Io. It wasn't a glitch, it was a volcanic plume, erupting with such ferocity that it was launching material 300 kilometers into space. Overnight, our understanding of planetary science was rewritten. Io was not dead. It was an inferno. But how? How can a moon, a fraction of the size of Earth, generate enough internal heat to sustain hundreds of active volcanoes, massive lakes of liquid magma, and geological transformations so rapid that its surface maps become outdated in a matter of years? The answer lies not in radioactive decay, which heats the Earth's core, but in a brutal, invisible game of cosmic tug-of-war. Io is trapped in what astrophysicists call a Laplace resonance. It shares a precise orbital rhythm with 2 of its neighboring moons, Europa and Ganymede. For every one time Ganymede orbits Jupiter, Europa orbits exactly twice, and Io orbits exactly 4 times. This perfect mathematical synchronization means that at regular, predictable intervals, Europa and Ganymede align with Io, giving it a repeating gravitational tug, pulling its orbit into an ellipse rather than a perfect circle. If Io were orbiting a small planet, this might not be catastrophic, but Io orbits Jupiter, a gas giant so massive it dwarfs all other planets in the solar system combined. This creates a tidal force, but not one that pulls on oceans of water like the moon does to Earth. Jupiter's gravity pulls on solid rock. Imagine taking a thick piece of wire and bending it back and forth over and over again. If you touch the bend, it will be burning hot from the internal friction. This is exactly what is happening to Io. The solid rock of the moon's surface is forced to bulge up and down by up to 100 meters, or over 300 feet, every single day. This relentless, crushing mechanical flexing generates an unfathomable amount of internal friction. The solid rock of the moon's mantle melts, transforming the interior of Io into an ocean of boiling magma. This is tidal heating, the invisible engine of destruction that powers the most hellish landscape we have ever discovered. Because of this immense subterranean pressure, the magma has to find a way out. But unlike Earth, Io does not have tectonic plates. Our planet releases its internal heat efficiently through the boundaries where continental plates pull apart or crash together, creating deep ocean ridges or volcanic arcs like the Ring of Fire. Io lacks this pressure release valve. Its crust is a solid, unbroken shell of sulfur and cold rock. Because there are no tectonic boundaries to let the heat escape gradually, the magma behaves like water in a pressure cooker with a blocked valve. It forcefully blasts its way upward through the weakest points in the crust, creating hundreds of hyperactive volcanic vents. This mechanism results in a landscape that defies human comprehension. The lava erupting on Io is primarily composed of molten silicates, similar to the basaltic lavas found in Hawaii or Iceland, but it erupts at temperatures far exceeding anything currently seen on Earth. Some of these magmatic eruptions are so incredibly hot that they glow fiercely in the ultraviolet spectrum, reaching temperatures of over 1200 degrees Celsius. But if the lava is silicate, why does Io look so profoundly bizarre? Why is it painted in brilliant shades of yellow, red, orange, and white, earning it the nickname the Pizza Moon? The answer is sulfur. While the underlying engine and the majority of the lava are silicate rock, the entire surface of the moon is coated in a thick frost of sulfur and sulfur dioxide. When immense heat from the silicate magma interacts with this sulfur-rich surface, it creates a spectacular chemical reaction. Sulfur changes color depending on its temperature and how rapidly it cools. When it is superheated and erupts as a gas, then rapidly freezes in the vacuum of space and falls back to the surface, it forms a bright red ring around the volcano. As it cools further, it transitions to orange, then yellow, and eventually to a pale greenish white. The surface of Io is essentially an ever-changing canvas, constantly being painted and repainted by the chemical fallout of its own violent eruptions. One of the most terrifying and awe-inspiring features on this world is Loki Patera. Loki Patera is a massive lava lake, over 200 kilometers across. The surface of this lake is a crust of cooling lava. But because solid lava is denser than liquid magma, eventually the crust becomes too heavy to float. It fractures, and a wave of sinking rock spreads across the entire lake, violently exposing the raging, glowing liquid magma underneath. This massive overturning event releases a blinding flash of infrared energy that our telescopes can detect all the way from Earth, before a new crust forms and the violent cycle begins again. But volcanoes and lava lakes are not the only anomalies here. Io features some of the tallest and most bizarre solitary mountain peaks in the solar system. Consider the Steeple Mountain, or the towering Buo Sole Montes, which reach heights of nearly 17 kilometers, dwarfing Mount Everest. How do these massive structures exist on a world without colliding continents? The answer is deeply tied to the moon's constant volcanic resurfacing. Because Io is continuously erupting, millions of tons of new material are constantly being deposited on the surface. This means that the older crust is constantly being buried deeper and deeper. As this crust sinks toward the hot mantle, the sphere of the moon internally shrinks. Imagine the skin of an apple wrinkling as it dries and shrinks. As Io's deeper crust is forced into a smaller and smaller volume, massive horizontal compressive forces build up. The pressure becomes so unimaginably intense that eventually something has to give. A massive fracture occurs, and a colossal block of solid rock is brutally squeezed and thrust upward, breaking through the surface like a jagged tooth. These mountains do not form in long, sweeping chains like the Andes or the Himalayas. They are violently extruded, isolated shards of the crust, solitary monuments to the incredible pressure crushing the moon from within. For years, our knowledge of these processes came from distant observations or brief, fleeting flybys. Studying Io up close is a logistical nightmare because the moon orbits deep within Jupiter's radiation belts. Jupiter's magnetic field acts like a giant particle accelerator, trapping electrons and ions and whipping them around at nearly the speed of light. Any spacecraft that gets too close is bombarded with radiation so intense it can fry computer circuits and destroy instruments in a matter of minutes. However, humanity recently found a way to peer closer into the fire. NASA's Juno spacecraft, originally launched to study the deep atmospheric interior of Jupiter, completed its primary mission and was granted an extension. Juno is a technological marvel, an armored tank of a spacecraft whose vital computers are housed within a massive, solid titanium vault to protect them from Jupiter's radiation. In late 2023 and early 2024, mission controllers executed a daring series of maneuvers, adjusting Juno's orbit to bring it within 1,500 kilometers of Io's blistering surface. The data and images sent back from these extreme close encounters have been nothing short of revolutionary. Juno provided us with the highest resolution images of Io in decades. We finally got a clear look at the moon's polar regions, which are vastly different from the equatorial zones. We saw the glassy, mirror-like surfaces of the cooling lava lakes, confirming that parts of the crust are indeed smooth as glass, before they fracture and sink. The Jovian infrared auroral mapper, an instrument on Juno, managed to map the thermal signatures of the volcanoes with unprecedented clarity, showing us exactly where the heat is escaping, how the magma chambers might be connected, and giving us a real-time snapshot of a world caught in a perpetual state of volcanic churn. While the Juno mission has vastly expanded our understanding of gravity, tidal heating, and the extreme volcanism of Io, the priorities of planetary science are shifting toward the search for extraterrestrial life. Future flagship missions like Europa Clipper and JUICE will head to Jupiter's icy moons, Europa and Ganymede, to explore their hidden oceans and potentially habitable environments, leaving Io without a dedicated observer. Yet, even as our cameras turn away, this isolated engine of fire will not fall silent. Locked in its brutal gravitational dance, Io will continue to overturn lava lakes, push mountains toward the stars, and rocket sulfur plumes into the void, maintaining its chaotic, unimaginable beauty in the dark. Io is a stark reminder of the terrifying power hidden within the cosmos. If you want to continue exploring the universe's most extreme and hellish worlds with us, make sure to hit that subscribe button, leave a like, and stay tuned for our next cosmic journey.